Welcome back, guys. This is the continuation of transport phenomena under diversity of a gas mixture. In the last video, we mentioned the concept of transport phenomena. We explained it. We mentioned the types of transport phenomena, which is mass transfer, momentum transfer, and heat transfer, and also their coefficients. So we discussed about the estimation of diffusivity, which is the coefficient of mass transfer, and under the estimation we solved the calculation under it, which we made use of the various correlation used in determining the diffusivity. So here is the next question, which states that predict the diffusivity for an equivalent mixture of nitrogen and ethane at 288 Kelvin and 40 atm using the value of diffusivity at 1 atm from table 17.1/1 alongside with the chart. So what they are insinuating is we should use the value of diffusivity at 1 atm to determine the value of this mixture at 40 atm. So this table, which is table 17.1, is on the property table of transport phenomena. Is it? So you can see it here. You can see the first column as column for gas and gas mixture, sorry, and the second column for temperature. The third column is for diffusivity, and the last two columns is for the mole fraction or mole ratio. So here we've been told that the mixture is what equimolar mixture. That means their mole ratio are equal, they are the same. Okay, let's start solution. Yeah. So you are going to determine this diffusivity at 1 atm now on this under this table. So you can see corresponding to nitrogen and ethane mixture now. So that is for the first column at the gas pair. You can see this mixture there. So the diffusivity of it corresponding to it, diffusivity AB will equal to 0.148 centimeter square per second. That is at the third column, check corresponding to nitrogen to ethane mixture. So check the corresponding temperature here. We can see that the corresponding temperature, that is T1, label this as diffusivity AB1, and label the temperature, outer temperature, as what? T1, which is what? You can see it as 298.2 Kelvin. The next thing we are going to do is to standardize this diffusivity at what? This given temperature. Note that is the first step we are going to take. So standardize this diffusivity as this temperature. So to do that, we are going to make use of Slate equation. So using Slate equation, we have diffusivity AB1 equal to A into bracket T2 over delta or raised power of B, and we have, that is equation 1. We have diffusivity AB2, that is diffusivity we are standardizing to at this temperature, equal to A into bracket T2 over delta all raised to power of B. That's equation 2. And we all know that A, B, and delta are constant. So next is to divide equation 2 by equation 1. Dividing equation 2 by equation 1, we have diffusivity AB2 over diffusivity AB1 equal to A into bracket T2 over delta raised power of B divided by A into bracket T1 over delta all raised power of B. So since A is constant, they will cancel out. B is also constant. Sorry, delta is also constant, they will cancel out. So what we'll be left with is what? T2 over T1. So since they have the same power, they will take only one, which is what? Raised power of B. So we are going to substitute the value in now. So get the diffusivity AB2, that is residing at temperature of 288.2 Kelvin. So we making diffusivity AB2 solve formula, we have it as dAB2 equal to dAB1 multiplied by T2 over T1 all raised power of what? B. And we know that B is equal to 1.823, which is constant, right? So the next thing is to what? Substitute the value in. So let's substitute the value in. We have diffusivity AB2 equal to this diffusivity, that is the diffusivity we got from the table 17.1, which is 0.148 multiplied by T2 is the what? Temperature we are standardizing to, which is 288.2 divided by T1, which is what? Temperature from the table 17.1. The outer temperature corresponding to what? This diffusivity AB1, which is 298.2. All raised to power of B, which is 1.823. So from here we have it as what? 0.139 centimeters square per second. So this what we have while standardizing it at what? 288.2 Kelvin. So the next step is to predict the diffusivity of nitrogen to ethane at 40 atm. The first step is to standardize it at what? The given temperature. So the second step is to what? Standardize it at the given pressure, which will be our final answer. So in this, we will make use of what? Generalized chart for self-diffusivity. That is using generalized chart for self-diffusivity. So this chart plotted what? Pressure multiplied by diffusivity divided by initial pressure multiplied by initial diffusivity against reduced pressure and reduced temperature. So and this reduced temperature and reduced pressure are given as reduced pressure is equal to actual pressure over critical pressure, and reduced temperature is given as actual temperature over what? Critical temperature. So this critical pressure is equal to summation of the mole ratio of individual multiplied by the critical pressure of individual gas, which is equal to mole ratio of A multiplied by the critical pressure of A plus mole ratio of B multiplied by the critical pressure of B. The critical temperature of the mixture is given as summation of mole ratio of individual gas multiplied by the critical temperature of individual gas, which is equal to mole ratio of A multiplied by critical temperature of A plus mole ratio of B multiplied by the critical temperature of B. So from here we have to determine the critical temperature and pressure of individual gas. So making use of this property table, we have gas, critical pressure, and critical temperature. So we have nitrogen and ethane. Let nitrogen be A and what ethane equal to what B. So the critical pressure of nitrogen is 33.5 and the critical pressure of ethane is 48.2. The critical temperature of nitrogen is 126.2 while the critical temperature of ethane is 305.4. From here we have to calculate the critical pressure and the critical temperature of the mixture. Here we have the critical pressure as what? XA multiplied by PCA plus XB multiplied by PCB, which is equal to XA. They say what they are equimolar. From the question, they say they are equimolar mixture. That means their mole ratio are equal. That is mole ratio of A equal to mole ratio of B. And mind you, the total mole ratio in a mixture must be equal to 1. That is XA plus XB equal to 1. That means what? XA equal to XB equal to 0.5. That means XA and XB they are 0.5. So from here we can substitute it in. That is XA, which is 0.5 multiplied by PCA, which is critical pressure of nitrogen 33.5 plus XB, which is 0.5 multiplied by critical pressure of ethane, that is 48.2. So we have it as approximately 1 atm. So we are going to calculate the critical temperature of the mixture. That is Tc equal to XA TCA plus XB TCB is equal to XA equal to 0.5 multiplied by TCA, which is 126.2 plus XB, which is 0.5 multiplied by TCB, which is 305.4. So here we have it as 1.3 Kelvin. Sorry. We have this as 40.85. And we have this as 205.8. Sorry, my calculator was on another function. That is why. So the next thing is to calculate, since we have gotten the critical pressure and temperature of the mixture, we are going to calculate the reduced temperature and reduced pressure. To calculate the reduced pressure, we have the formula as reduced pressure equal to actual pressure over critical pressure. And actual pressure from the question is 40 atm over the critical pressure, which is 40.85 atm. 40.85. So we have it as approximately 1 atm. No unit is dimensionless. We have it as approximately 1. So the reduced temperature is given as actual temperature over critical temperature, which is given as, we have the actual temperature as 288.2 over the critical temperature, which is 215.8. So this will give us 1.3. Yeah, this will give us 1.3, the dimensionless. So therefore, we have to substitute this into the generalized chart for self-diffusivity, which is P, the final pressure multiplied by the final diffusivity over the initial pressure multiplied by the initial diffusivity against reduced pressure of what? 1 atm and reduced temperature of 1.3. So we have it as, we are going to make use of generalized chart for self-diffusivity. So this is the chart. You can see the vertical column as I have explained it in the other part. You can see the vertical column as for diffusivity, the horizontal column as for reduced pressure, and the curves is for what? Reduced temperature. So at the horizontal axis, which is at reduced pressure, you can see 1 atm there. You can see it as 1 there. You can see 1 there. So check the curve, you can see 0.3. So you have to intersect it. So as we intersect it, you check it corresponding to diffusivity at the level which at the particle axis. So you read it. I have it as 0.84. So it's not actually necessary for us to have the same value. So you might see it as 0.83 or 0.85 or 0.82. It might not actually be the same view. So everything is still correct. So from here, I have to make the diffusivity, the final diffusivity we are looking for, subject of formula, which is diffusivity AB equal to initial pressure multiplied by initial diffusivity multiplied by this value we got from the chart, 0.84, divided by the final pressure. This is how to make it subject formula. So substitute the value in. We have initial pressure as 1 atm. That is, the pressure from the table is 1 atm multiplied by the diffusivity, initial diffusivity. That is, the diffusivity we standardize at the temperature of 288.2, which is 0.139 centimeters square per second, multiplied by the value gotten from the table, from the chart, 0.84, divided by the final pressure, that is pressure from the equation, which is 40 atm. Right? From here, we have it as 2.92 times 10 raised of minus 3 centimeter square per second. The estimated diffusivity of an equivalent mixture of nitrogen and ethane at 288.2 Kelvin and 40 atm, using the value of diffusivity at 1 atm from table 17.1 alongside with the chart, is what? 2.92 times 10 raised of minus 3 centimeter square per second. So this is the solution to this question. So see you in the next video. Don't forget to like, subscribe and share. Thank you so much.